Welcome friends, Igor is here, and in this video we will prove that every linear system has no solutions, one solution, or infinitely many solutions. In this lesson we will see that there are only three possible types of solution sets of a linear system. We will establish that a consistent system with more variables than equations automatically has infinitely many solutions. And we will learn an important lesson, that is, to pay attention, careful attention, to the assumptions in the statement of the theorem. First, we are going to investigate how many solutions a consistent linear system may have. Suppose we have a consistent linear system with n variables, and let A be the augmented matrix of this system. Also, let B be the reduced row echelon form of the matrix A, and we are going to assume that B contains R pivot columns. Then R must be less than or equal to n, and moreover, if R is equal to n, then the system has a unique solution, and if R is less than n, then the system has infinitely many solutions. I always recommend that before jumping to prove the theorem, you should pause and ask yourself, what is it that I need to prove? Then you should carefully read the statement of the theorem again, and now we see that in fact there are three statements to prove. First, if a linear system with n variables is consistent, then R cannot be more than n. Second, if R is equal to n, then a consistent linear system has a unique solution. And finally, if R is less than n, then a consistent linear system has infinitely many solutions. Now that we know exactly what we are looking for, we are ready to start proving. First, let's prove that if a linear system with n variables is consistent, then R is less than or equal to n. If the linear system has n variables, then the augmented matrix has n plus 1 columns. Because the matrix B has n plus 1 total columns, it cannot have more than n plus 1 pivot columns. And this automatically gives us the condition that R is less than or equal than n plus 1. But this is not enough, because we want to show that R does not exceed n. What I'm going to do next is I'm going to show that R cannot be equal to n plus 1. I am going to use a proof by contradiction. If R is equal to n plus 1, then every column of B must be a pivot column. Then the last column of B must also be a pivot column. But we already know that if the last column of the reduced row echelon form of the augmented matrix is a pivot column, then the corresponding linear system is inconsistent. This is a contradiction with our assumption that the linear system is consistent. And this contradiction shows that R cannot be equal to n plus 1. So, if R is less than or equal to n plus 1 and it cannot be equal to n plus 1, R is strictly less than n plus 1. Therefore, R is less than or equal to n. Now, let's prove that if R is equal to n, then a consistent linear system has a unique solution. If the system is consistent, then the last column of B cannot be a pivot column, and therefore all pivot columns correspond to variables. There are pivot columns and n variables. If R is equal to n, it means every single variable corresponds to a pivot column. Therefore, there are no free variables and all variables are the dependent variables. And that means this system has a unique solution, which can be obtained by setting every dependent variable equal to the entry in the last column of the reduced row echelon form. Finally, let's prove that if R is less than n, then a consistent linear system has infinitely many solutions. Once again, because the system is consistent, the last column cannot be a pivot column, and therefore all pivot columns correspond to variables. we have r pivot columns and n variables. When r is strictly less than n, we have at least one free variable. And because we have at least one free variable, we automatically have infinitely many solutions, because free variables can assume any values, and there are infinitely many possible values for them to assume. Now we are ready to prove the first big theorem in this course. There are only three possible solution sets for any linear system. A linear system has no solutions, a unique solution, or infinitely many solutions. We already have all the ingredients necessary to put together this proof. We start with a given linear system. We construct the augmented matrix of this linear system, and we apply the Gauss-Jordan elimination to obtain the reduced row echelon form of the augmented matrix. Then we look at the last column of the reduced row echelon form. If the last column is a pivot column, then the system is inconsistent, and it means the system has no solutions. If the last column is not a pivot column, then the system is consistent. But if the system is consistent, we just proved that r cannot be more than n. And if r is equal to n, then the system has a unique solution, and if r is less than n, then the system has infinitely many solutions. Therefore, there are only three possibilities on the solution sets. There is one way to guarantee that a consistent linear system has infinitely many solutions, and this is when there are more variables than equations in the system. To prove this claim, let's suppose we have a linear system with m equations and n variables. Our assumption is that n is greater than m. Let B be the reduced row echelon form of the augmented matrix of this linear system, and let's assume that B has r non-zero rows. Because B has m rows in total, r cannot be more than m. But we also assumed that m is strictly less than n. If you look at the beginning and the end of this inequality, you will see that r is less than n. And we already proved that if you have a consistent linear system with r less than n, then this system has infinitely many solutions. Let's look at an example. We have a linear system with 3 equations and 4 variables, so there are more variables than equations in this linear system. Yet this linear system is inconsistent, as you can see from the reduced row echelon form of the augmented matrix. The last column is the pivot column. But wait a minute. Didn't we just prove that if a linear system has more variables than equations, then it has infinitely many solutions? How come there are no solutions in this case? What we missed in our excitement is one key assumption. That theorem applies only to consistent linear systems. It preassumes that you start with a consistent linear system, and only then, if you know that the system is consistent, you can look at the number of variables and the equations. I hope this example allows you to learn a valuable lesson. Be careful when applying theorems. Please pay attention to all assumptions in the statement of the theorem because they are essential. If you found this video useful, please like and subscribe to help others discover this content. In the next video in this series, we will talk about homogeneous linear systems. I will see you later.